Hi everyone, so today we're going to be continuing on with our alkanes, and we're going to be looking at cycloalkanes. And so these are the steps that we have to follow with naming, and it's really important when we're naming we follow all of these steps. So it's very similar to what we talked about yesterday. We have to identify the longest carbon ring, that is the root name, that's the parent chain. From there we identify all groups attached to it, and then we have to number the carbon atoms in order to give the lowest possible numbers. And then once again, if there's two or more groups, then, and the numbering is a tie, then the group that comes first alphabetically gets the lowest value. So our first example here, we're going to go through a few of them. We need to identify a few things. We need to identify the longest carbon ring, as well as the groups attached to it. So we can see that it is a square. So if it is a square, we know that that is butane because of information that we learned yesterday. So always reference the chart from yesterday. Attached to the parent ring is our group, which here we have methyl, and we can see that there. And then we have to number, and there's only one group, so therefore we can just easily number. The group always gets the 1, and then you can go in any direction in order to number it. From there, we have to identify and name it. So because the methyl is on 1, we're going to write 1-methyl. Because it's a cycloalkane, we have to write cyclo because we need to know that it is complete. And then butane. And the butane means that there's 4. Next example here, we have 2 groups that are attached. We have a methyl and we have an ethyl, and because the ethyl is alphabetically first, we're going to number it as 1, and then we're going to go in the direction of our next group. So 1, 2, 3, 4, 5, and then we're just going to name it from there. So ethyl's on 1, so 1-ethyl, methyl's on 3, methyl, and then it's a cyclo. And then because it's 5, it is pentane. So make sure that we always identify all the different parts of it using the rules from the previous slide. Now we're going backwards here. Not yet. We're given still the structural drawing, so we still have more here, but this one's a little bit more complex. So we have 3 different groups off of our long parent chain. And based off of this is bromo. And then these 2, we have methyls. But because there's 2, they're dimethyls. So alphabetically, bromo goes first. So we're going to number that as 1. And then the next is methyl, which is this methyl that is closest to it. So we're going to number in that direction. So now we're going to name it. So bromo's on 1. So 1 bromo, and then our methyl is on 3 and 5, and it's a dimethyl because we know it's 2. And then once again, cyclo. But remember, because there's cyclooctane, we're only going to write the 1O, and then add octane. We don't have the O's together. Okay, so that is how we obviously write our name for it. It's really important to recall back to when we are naming our compounds that if they are 2 vowels, they don't go side to side. Now we're going opposite here. So we're given the name and we have to draw the structure out. So we're going to start off usually going backwards in the situation. So butane, we know that's going to be a square. So we're going to draw a square out. Okay, you can number it however way you want. So I'm just going to number it how we did the first one. And then from there, we can draw out and write out where they're going to be located. So we're going to have an ethyl on 1 and then a propyl on 2. And ethyl is CH2, CH3. And then our propyl is going to be CH2, CH2, CH3. Okay? So now I want you to try out these on your own. Try it out, pause, and see what you can do. This one here is a halogen. So do take that into consideration. All right, so hopefully, oops. All right, so hopefully you understand where all the information came from. So number 6 is a tricky one because it's a halogen. We have chlorine, and the chlorine is 3 of them on different locations. 2 is on the first section, and then 1 is on the second one. So do take that in consideration, and then you just have a methyl on 3. We know it's cyclo and butane, and that gives us 4 spots. So those are cycloalkanes. There are some properties of alkanes that are really important. So since the carbon-hydrogen bond is going to be very close to being nonpolar because of the electronegativity difference between carbon and hydrogen, it is considered to be nonpolar. So all hydrocarbons are nonpolar. So because of its nonpolar, the van der Waals forces are the main intermolecular forces in the hydrocarbons. So intermolecular forces, remember the difference between inter and intramolecular forces. It's very important to recall. So intermolecular forces is going to be different than intra. So intra, remember, is the forces that are within the molecule that bond the atoms together. So it's between the atoms within that molecule. So these are our forces here. Inter is just between 2 molecules that hold it together. So they are going to be an intramolecular, it's going to be not an intra, it's going to be an intermolecular forces for van der Waals in order to hold it all together. Okay? So when we look at forces, okay, so hydrocarbons are nonpolar. The London forces are nonpolar intermolecular forces. Okay, nonpolar. So that means the melting point is the point where the solid is going to become liquid. So in a situation like this, we're going to be absorbing all the energy and heat in order to overcome the intermolecular forces that are going to occur. Okay, so we need to make sure that we have a certain amount of energy absorbing in order to gain heat and go from a solid to a liquid. So that's its melting point. Its boiling point, we can recall, is where a liquid becomes a gas. So once again, we have to absorb that heat or energy to overcome the intermolecular forces between molecules in the liquid form for this to occur. Okay, so we're absorbing heat for melting and boiling points. So London forces, these nonpolar intermolecular forces, are very, very weak. And so therefore our hydrocarbons, which we just talked about, are going to have a very low melting point. These nonpolar, intermolecular forces, which are the forces between molecules, are going to have very low melting and boiling points. So you can see all the different ones that we've taken a look at. So methane has a certain melting and boiling point. You can see that there. But then as we go down to decane, you can see that the more complex the structure is, then the higher the melting and boiling points are. So very interesting to see and very important to note that these are London forces and they're going to be very weak. So as we get a longer chain, the more surface area and therefore the more sites for electron to electron interactions, and that's where we have the London forces are increasing with the increased chain length. So we know that when we have ethane, we only have a double bond. We can have a triple bond. You can see these forces are getting stronger and stronger and stronger because it's longer and more complex. So if the chain gets longer, such as like decane, then both the melting and boiling point increases. So It is very much dependent on how long the chain is, the more complex the structure is, and that's where we have a higher melting and boiling points. So when we use this property to separate mixtures of alkanes using fractional distillation, so that is a process where we're going to be using oil that's in oil refineries that separate lighter fractions of crude oil, such as natural gas and other fuels, from heavier fractions that are used to make waxes and asphalt. So fractional distillation is a process of separating our mixtures. Okay, so what they do is during this process, the temperature of the mixture of hydrocarbons is slowly increased. So when we increase the temperature, then we're able to separate them because the more complex structures we're able to separate with different temperatures. So once we reach that boiling point, the alkane boils out of the mixture and then the chemist collects the vapor and condenses it. So here you can see the image of fractional distillation. So you can see based off of different amounts and different temperatures, it's a little blurry, but you can see kind of here that each gas has to reach a different temperature in order for it to condense. So if we have lighter alkanes, so those are the ones that have smaller boiling points, such as methane, those are going to have smaller boiling points because of their weaker van der Waals forces, and they are going to be seen to separate last because they don't need as much heat. The heaviest ones, the ones with the longest, like decane, are going to be separated first, and they need to be closest to the heat in order to reach their melting or boiling point. So once again, the smaller the alkanes, such as methane and ethane, are going to be highly flammable, and then the larger ones are going to be more difficult to ignite, and so they have to be vaporized first, okay, because of their size. So, very important information. Now we're going to look at alkyl halides, which are halogen alkanes, and these are different type of alkanes that contain halogens, such as chlorine or fluorine. So when we look at these, they do not react with acids, bases, or they do not react with different ways. So when we look at our alkyl halides, they can be formed by substitution reactions. We're going to take a look at this more in a minute. But on this slide here, when we look at alkanes as a whole, they are seen to be fairly unreactive. So they do not react with acids, bases, or strong oxidizing agents. So because of their unreactivity, because they're not reactive, they have to use lubricants, and this is important for when we make plastics. So this is going to be very important because alkanes are very important in our everyday life. They're used as fuels because they have a large amount of energy, which is thermal energy. They also have carbon dioxide and oxygen that are important during complete combustion. So in complete combustion, we're going to take a look at complete combustion of butane, so C4H10. And so when we look at the thermal energy in order to have a balanced equation, we need to look at, is it going to be a reactant or a product? So if we were going to look at our complete combustion of butane, so we have C4H10 plus O2, that's going to react to produce CO2 plus H2O, and then on top of that, it will produce thermal energy. Okay, obviously this is not balanced, so we always have to make sure it is balanced. But thermal energy is going to be a product. Okay, so when we look at these alkanes, so this is what I was mentioning before, the smaller the alkanes, such as methane and ethane, they're going to be very flammable. The larger alkanes are going to be more difficult to ignite, and they must be vaporized first before igniting everything because we need to make sure that we get rid of them because they are requiring more energy because of their size. So once again, because of that, we have different hydrocarbons that are going to release different quantities of energy per mass when they burn because of the size that they are, and therefore it's going to impact things differently. And they also need their own special treatment. When we look at CO2 and H2O, these are greenhouse gases, and they help keep the earth warm by reducing the amount of sun's heat that is reflected back into space. But CO2 does contribute to climate change because we have too much of it. So this is where I was talking about the alkyl halides, which is our halogen alkanes. So I mentioned this a little bit before. These are really important because the alkanes, they contain halogens, which we saw before in our examples. And so when we look at alkyl halides, they can be formed by substitution reactions, where our hydrogen on the alkane is substituted for a halogen, and we saw this a little bit yesterday. So they contain two different halogens, and both are going to be used and contain both chlorine and fluorine in this situation. So we have chlorofluorocarbons, and that is where they contain both chlorine and fluorine. So for example, you can see here we are combining chlorine with our alkyl, and then it creates obviously our products with both chlorines in it. So when we look at the polarity of the alkyl halides, it's really important to look at how it is structurally. And so since the halogens are more electronegative than carbon and hydrogen, that means the bond to the carbon atom in the hydrocarbon or chain, they're going to attract the electrons in the bond away from that carbon atom because they're more electronegative. They're going to pull things more. So when we look at the bonds here, normally our carbon chain has something attached to it. That X in this situation is any halogen. So it can be chlorine, bromine, fluorine, iodine. So anything like that, that is all going to be a part of our alkyl halides because it's going to be attached to our carbon chain, and it's going to be more electronegative, and that's really important to remember. So because of the halogen and its bond, the halogen is partially negative, and then the carbon becomes partially positive, and you can see that on the image here. So here the X is our halogen. This is our parent strand. And then we have partially positive and partially negative. The reason why it's partially negative is because it has electrons. It's pulling the bond, and that's why it's partially negative. We know that when we gain electrons, we become more negative. So because these molecules become polar, this increases the intermolecular forces, and that makes their melting and boiling points higher than any of their other alkanes. So our alkyl halides are going to be very, very, very strong with their electronegativity, and they're going to have higher melting and boiling points because we need to pull it away. So for example here, we're going to look at butane. Butane has a boiling point of -1 degree Celsius. We can see the bond here, but when we have chlorobutane, so we know that there is a halogen added to it, this boiling point is going to be much higher, and we need to make sure that we are able to break this bond up, and so we have to have a higher boiling point because of the electronegativity forces that are within a halogen here. So once you add the halogen, the temperature automatically increases, and it makes the melting and boiling point much, much higher. Okay, so you can just see, just with the little halogen added, it changes everything. So you're going to take a look at some homework. So complete page 17 and answer questions 1 through 9, and then try out, write the balance equation for the complete combustion C6H12, very similar to what we just did before for butane. I want you to try this one out and make sure that it is balanced. Add the subscripts of the precipitate, see if you can get it correct. Okay, so